We are very happy to have our second speaker for today, Sylvain Crovisier. And the title is Existence of Physical Measures for Smooth Surface Diffeomorphism. Please. Existence of physical measures for smooth surface diffeomorphism.
Thank you. Thank you a lot for the invitation. It's my pleasure to be here. I will talk about joint work with Jérôme Buzzi and Omri Sarig. So it's part of a long project we have together. So there are several papers. So what I will present is a consequence that we got about this project. But Jérôme will come next spring and will give a mini course here. So he will talk about part of this project, more about the technique. So maybe this talk is an advertisement for his mini course. Okay. So the question I would like to discuss today is about the existence of physical measures. So when you have a dynamical system, one question is to describe most of the orbits, the statistic of the orbit of most of the points, and then you come the notion of physical measures. So in the setting for today, we have a diffeomorphism. It's smooth dynamism, a diffeomorphism on a closed manifold, connected manifold. So what is a physical measure? So you take an invariant measure, probability. So it's a physical measure. If it has a large basin, so if its basin has positive volume, so what is the basin? Near U is the set of points whose forward orbit distributes against U. So you look to this sequence, to these sequences. So you take the Dirac measure along the first iterates. And there's sequence, there's special measure associated to X, you call them the empirical measures, and you require that they converge to mu for the Greek topology.
Generic.
Yeah, typical for the measure, generic for the measure. So let me give some example. So the question is, do we have such a measure for a system? So sometimes yes, sometimes no. So some example of existence. So well, you take a peak. You have a fixed point, so, which attracts orbits in a neighborhood. Another example is the case of, so you may take the volume. It's for conservative system. Such that the volume is ergodic. In this case, the volume is an invariant measure, such that almost every point is generic. And for non-existence, well, you may also have some conservative system without ergodicity. For instance, you may consider the identity map. In this case, each point is fixed, and so can only converge to its Dirac, and so the basin has a zero volume. And another famous example is Bowen A. So you may build a system like that. So you have two fixed points with whose separate two saddles whose separatrices coincide. And so you have an invariant region here, and inside the orbits accumulate on the cycle. And you may build the example in such a way that the orbits here, sometimes are close to this point or close to this point, but they don't know which point to choose. So when you look to the distribution, sometimes you're close to this Dirac, sometimes here, and so you don't know that. Okay. So let me discuss the problem of existence. So some existence results. So let me first start with a very classical setting. So a good case is a case of uniformly hyperbolic system. So you have another maps or axiom A map, or in this case you have a classical theory by Bowen, C9, Ruel Bowen. So for instance, you have the another map where transitive diffeomorphism uniformly hyperbolic. So the map on T2, you know well, or you may have an attractor. So you will have attractors which are foliage laminations by some manifold along which the dynamics stretches, and transversally you contract. Okay. And so for the system, the tangent space splits into two sub-bundle invariant continuous, one contracted, one expanded. Then you have a more complicated situation. So one setting is a setting of critical dynamics. So what I mean by critical, it means that you cannot decompose in two directions like that. And the famous example is given by the Taylor map in factors, and then you have deep results starting with Benedict and Carlson. Then the people who built for large some set of parameters. So this is a family, this parameters family. So for some set of parameters, there is a unique physical measure. Another kind of system are partially hyperbolic system. So here you have a decomposition. Excuse me, what do you mean by critical? I mean that you cannot decompose the tangent space as two invariant bundled continuous. Mm-hmm. So a way to characterize the lack of decomposition is to define a notion of critical point. And so on surface, you have a dichotomy, either the critical set is non-empty, or you have a decomposition. It's a way to present it. So here you have a decomposition, I think in a higher dimension, but you don't have good contraction or expansion. So let's assume you have one of the bundle is uniform and the other one not. But you replace by some non-uniform weaker notion of contraction or expansion. And so you have words starting maybe with
CS or CU?
Or CU, yes. Thank you. Alves, Bonanti, Viana. Many other words. Okay. So here you have the decomposition, but not the uniform. Okay. So in all these examples here, the measure, the physical measure you find, not only satisfies this property, the physical, but also has a good geometrical property structure that I will explain later, which is a property that we call the Sinai-Rued-Bowen measure. So the goal is to try to find criterion that ensure the existence of physical measure, but inspired by some hyperbolicity. So we define a weaker notion of hyperbolicity and hope that it foresees the existence of such measure. So let me introduce some non-uniform hyperbolicity. So we say that a point X has admits Lyapunov exponent. So we are in dimension, let's say D. We have D numbers. If there are vectors that are linearly independent, what X, so that when you look to the growth of each of them, and take the exponential growth rate, and this admits a limit which is equal to lambda I. So there is an X in this. X is here. I look to okay. Yes.
Don't you want to also say on backward?
But here, for the frame I'm discussing, I am looking at forward times, but
Then flag.
yes. So some numbers may coincide, and so you have. Yeah. Okay. Yeah, I have so
Not unique choice.
No, there is no unique choice for the field. Exactly.
Only there is a flag also.
Yeah. Yeah.
Okay. And almost everywhere, right?
No. I am just saying that a point admits the exponent. Okay. So when you're uniformly hyperbolic, there's lambda I never vanish, so they are negative along ES, positive along EU. So to keep some hyperbolicity, you will require to have many points whose Lyapunov exponent never vanish. So Viana proposed the following conjecture. To consider F a smooth diffeomorphism, smooth enough, And you look to the point, to the set, we call it non-uniformly hyperbolic set, which is a set of points which admits Lyapunov exponent and none of them vanish. Okay, so you assume that this set has positive volume. Okay. Then there is a physical measure. So this is his conjecture. It has been discussed by in many works. So some example of results for 1D maps, non-invertible. There is a positive answer, assuming negative Schwarzian derivative. It's the result by Keller. Yes, dimension 1. In any dimension for diffeomorphism, there is also an attempt. So for diffeomorphism in any dimension, but assuming some assumption of recurrence. That I don't want to describe. It said that this points here, you also require that this point here satisfies some good recurrence inside a set of where you have a good control of the Lyapunov exponent. So this is a work by Timenaga, Luzzato, Kessin, and then another work by Benovavia. And another work I may mention is a work I did for partially hyperbolic system so under partial hyperbolicity. But in this case, I assume that so you have a stable bundle, an unstable one, and in the middle you have a degenerate bundle which has dimension 1. Okay. So in this case, the answer is also yes. So this is a common work with Dawei Yang and Jinhua Zhang.
For flows.
So no, it's for diffeomorphism.
No, but if you have diffeomorphism for flow, then we send paper more.
For flow, you will recover. Yes. Yeah, you have a lot of. Yeah. So what do we work to prove in this work is the fact that in this setting, for almost every point, you always have a well-defined Lyapunov exponent in the center. And then points whose Lyapunov exponent are positive or negative should generate a physical measure. Okay. So what I want to present now is an answer to this question for surface. Okay. Any question? Okay, so here is a theorem. This guy, and this has been also proved by David Bergier. So now we consider F a infinity surface diffeomorphism. And we assume something a bit weaker. So we look to this set, the set of points such that so you look to the growth along the orbit, take the lim source, which always exists, and you assume it's positive. So you assume that this set has positive volume. Okay. So then F as a physical measure. Which in fact satisfies this geometrical property, I will recall it later, so it's an SRD measure. Okay. This is a result I would like to discuss today. So David Bergier has a proof which is different, and he could also control the basin of this so you may have several physical measures, but the basin of the physical measure, so it should cover the set X. So you get through the following: X is contained in the union of the basin of the physical measure up to zero volume. And another thing is that he discusses also the case where F is not infinity. So when F is CR, this is sometimes true, sometimes false. What you would need to show that it's still true for CR, you need that to consider points whose expansion is large enough compared to the smoothness. Okay. So the way to find a physical measure, or to show that a measure is physical, is to check this property that I will record now, which is a SRD property. So mu is an SRD measure. Let me assume that mu is ergodic. If it has a positive exponent, or you may look also to its entropy. So the entropy of mu is positive, and having positive entropy forces the measure to have some hyperbolicity, and so for typical points to have unstable manifolds. So at any point you have almost every point you have some manifold through the point that we call unstable manifold. You may have also a stable one. And on surface, that's it. In higher dimension, the dimension of this manifold maybe does not fit with the full dimension. So when you have curves like that in stable manifold, you may disintegrate the measure along the curves. So mu disintegrated along the unstable curves is smooth, is absolutely continuous. So this is a classical definition of SRB measure, but I will use another way, which doesn't require this definition. So you just look at the entropy of the measure, and you look at its. So you may, for an harmonic measure, you may also associate Lyapunov exponents, so D numbers. And so let's look at the maximal one. So this is the maximal Lyapunov exponent. So it just, if you take almost every point for the measure, it has the Lyapunov exponent, you take the maximal one, and it coincides for any choice of a point typical from the measure is a good. So you have these two numbers, so the entropy. And you have an equality. Okay. There are two characterizations, and I will work with this one. So you are on surface, real proved an inequality for any invariant measure, which is that the entropy is always less or equal to this exponent. Real. So that this is always so in this case we consider measures which are maximal for some property. Okay. And then
may I ask you?
Yes.
In the first condition, you said that the disintegrated measures are absolutely continuous.
Yes.
With respect to.
With respect to Lebesgue along the axillary.
So this is the case different from minus. Different from which are just
For a sink, you mean?
yeah.
So for instance,
but it's
for a sink, you don't have these conditions.
Yes, okay.
This condition is here just to ensure that you always have this that are not degenerating. Yeah. But keep this in mind. Okay, this I won't use. Okay, just some property. So classical property is that if mu, so let me focus on surface. Mu SRB on surface. Imply that mu is physical. Maybe for F C2 different. So this is a property by Le Bratier. So now I'm working with this condition to find physical measure. I look for measures satisfying instantly.
So continue with the relation sets.
What do you say?
It says that it's not here, but the key is here absolute continuity of stable.
I didn't see.
Behavior on unstable leaf
Yes.
is the same as behavior. Because you have stable Foliot absolutely confused.
Yes,
So the bank measure translates
exactly.
almost every fiber.
Yes. Yeah. To
This is the
to
key.
attract, so you want to attract almost every point in an open set, so or positive.
So Foliot.
So you have unstable manifold of typical point for the measure. Almost every point along this manifold is also typical for the measure and has a stable manifold
Also for these.
whose size is not uniform but will capture a set with positive measure in this region. This is what is behind. Here we have. Okay, fine. So,
Where did you use circle?
well, just because if I am in higher dimension, this definition allows the existence of third direction where the Lyapunov exponent may vanish, and I have no control along this direction. So in any dimension, you have a similar property. If you require that the measure is what we call hyperbolic, so no Lyapunov exponent vanish, and then that's fine. So how to check that you have an SRB measure? So there's two. So construction of SRB measure. So let me discuss first the very classical setting. So the case of uniformly hyperbolic system, another diffeomorphism. So let me just take F on T2, which is, well, you know, you have this map, which is hyperbolic. You perturb it, it's still hyperbolic. And you want to show that you have a physical measure, and sub-measure. Perturbation of this. So how is it? So you are on the torus. One way is okay. So the torus now is foliated by unstable manifold and stable manifold. So you take a curve, gamma is a piece of unstable manifold. So it's a curve so that when you iterate, it's stretched. And so one classical way to get the physical measure is to say, okay, I take the Lebesgue measure along gamma, I push by the dynamics, I take Cesaro as average, and then it will converge to a measure which is the SRB measure. So this is a classical proof of, for instance, P-9. And so when you iterate the curve, well, you will fill the manifold, and you have this convergence. I would like to do it in a different way that will be adapted to what we will do later. So instead to push the Lebesgue measure, I want to push single points. So I take a set of points here, I push, and I hope that when I look to their empirical measure, they converge to a same measure. So I will have to force that property by choosing a subset of points which have similar empirical measures. So let me do it just artificially. So I will do some extraction. So we will choose some subsets Tk inside gamma, and sometimes, so that will converge to infinity. So if I do that, now I will look to the empirical measure for this time. And starting from this point. So what I want is that when I do that, I find a measure that are about the same, that are all close to a same measure. Okay. How to do that? You just take the set of probability measure, it's a compact set, you split into small pieces, and then for each point in gamma, you push. So you have a finite number of subsets. You look to that you find, and you keep a set of the space of measure which is attained by many points, which are Tk. So you do it artificially. So of course the set Tk will be smaller when you require this empirical measure to be closer to a limit measure, to the same measure in UK. So you will enforce this condition. So you require, and then by extraction, you may also require that the mu k converge to mu, which is invariant. And here I have said about nothing. What I want now is a condition to say that the Tk are not too small. So we want the Lebesgue measure of Tk to decrease sub-exponentially. So for some So how do I do? I take for large k, I take the space of measure, I split it into many small pieces, and then as I said, and so the Lebesgue measure of the space Tk that I find is the size of gamma divided by the number of pieces in my space of measure. Okay, so this is what I find. So when I do that, I can require nk to be much larger. So, okay, I have divided my curves into some number of pieces. So this measure is not too large, but I may do it for a time which is much larger. So, so I find this one.
I think you lose. So.
Yeah. So it's completely artificial. You can always do that. And now let's see what we got. What we get. So now let me do some counting.
May I ask a question about the motivation in this testing scenario? Is it completely obvious that when you do this, it becomes SLD?
No, there is some work. I mean, you take the Lebesgue measure, you push, and when you push, you have, for instance, distortion argument that show that at any step it's still a smooth measure. The question is what happens when you take the limit. So you need to show you have a distortion argument which allow to show that the density do not degenerate along the unstable curves. And then
Okay, from transversal direction, you get it from the argument I thought. Attraction in this direction of image of this chosen interval. And here actually continue this trigger because you have just linear relation. When you take perturbation, then this should continue.
Okay, so let's do now, let's do something less trivial than that, maybe. So some counting. So let me consider this measure, and let me count the number of itineraries that we see.
So I think this point 3 way that you given K, you lose some percent, some short sequence of short intervals, and then something is left, and again for
Here the measure will come to 0. So it's yes.
yes, but you add some new intervals which are good for longer time. Yes, I tried to do it. No, maybe I'm wrong. Okay. You didn't explain how you get through, so let me know.
No, just allow to consider a set of points which is smaller and smaller, but you don't want to decrease fast. So now let me count. So you fix a scale, a small scale, and you count. So let me. So this is a number of itineraries at scale delta that one gets. So itineraries of length nk that one gets from the set tk. We have selected the set tk that we push for time nk, and we look at scale delta, how many different orbits we see. Okay.
So you take a partition into some cubes or size.
Yeah, you can do it in this way. So from below, you know that okay, you tk. So you start in a curve, in a small curve. And when you iterate, this curve is stretched, and has a, so this set here has some positive Lebesgue measure also. So this set grows at least like, so the size of your initial set, size along the curve, times how much you stretch. Let me observe that this quantity depends on the points, but since all these points are close to a same measure, and so this expansion can be computed as Birkhoff's average along for some continuous function, because you just look to the expansion along the unstable bundle, which is a continuous bundle. So this quantity is about the same for grows in the same way for all points in tk. So you have this lower bound, and then, well, you use for this quantity your lower bound, and for this, you know that it will grow like, so you look to the limit measure. The limit measure also has an asymptotic growth along a Lyapunov exponent, so along the unstable direction. So you have this lower bound. And now you also have an upper bound. And how is the upper bound? The upper bound is like the entropy of the limit measure times nu k plus some error that will go to 0 also. So, well, it's maybe similar to the proof of the. So, you know, when you fix a scale, the entropy of measures has some semi-continuity. And so here you pass to a limit. So this measure is not invariant, it's more and more invariant when k is large. And so you use the same argument as a semi-continuity of entropy at fixing a scale to show that you have this bond. So behind that, you see that the itinerary you have here should copy most of the time the itinerary of the measure. Okay. So you have these two inequalities. And so then what is the conclusion? So, yeah. So the conclusion is that this quantity here is smaller than this quantity. And so when you pass to the limit, you get that the entropy of mu is larger or equal to the upper Lyapunov exponent of mu. Okay. So maybe I should be say that mu here, I don't know if it's ergodic, so here it's an average Lyapunov exponent. It's the average of Lyapunov exponent of its ergodic component. So you found this inequality, and as Thomas said before, you also have dual inequality, which says the other inequality is always satisfied. So in fact, you have equality, and having equality says that any ergodic component also has the equality, satisfy the equality. Almost. And so this is the definition of SRB measure on surface. So one way to find an SRB measure. You see, with this notion of SRB measure, you have avoided differential tools. In fact, we didn't discuss the Bayesian. The Bayesian was controlled by this property. But once you know that, you don't really need too much of differentiable dynamics. And you have this way to build an SRB measure. Okay? So this was for the uniformly hyperbolic setting. And you may say, okay, well, let's try to do it for an arbitrary surface diffeomorphism. So where did I use a lot that I am uniformly hyperbolic? So the main place where I use it was to say that here we use that we have an unstable bundle which is continuous. And so this says that the Lyapunov exponent varies continuously with respect to the measure. With respect to the measurement, just because the Lyapunov exponent is obtained by integrating a continuous function, which is a log of the derivative seen along the unstable bundle. So this was crucial here at this step when we compared the expansion along the empirical measure with the expansion of the limit. Okay. So let's see what happens when we look for a general diffeomorphism. So a general how to modify that. So we don't know that the quantity converges, so we will force it also. So, take, what do we take? So we take, so you have this assumption that you have good growth on a set with positive measure. So you assume that you may find a curve such that when you iterate along the curve, you see some expansion for many points. So for a set of points with positive Lebesgue measure of gamma. So how is it? By assumption, we have a set X where we see some expansion. And then by a Fubini argument, if I pick a curve, I have this curve will, for many curves, for some curve at least, will meet the set X along the set with positive Lebesgue measures. It's almost what I want. But in fact, I can also, for a typical curve, the expansion, when I have the expansion at a point, in fact, this expansion is seen in almost all directions. So it's easy to also require that the expansion occurs when I iterate a vector tangent to gamma. I don't have to choose it. So we have this condition. And then I do the same. Okay. But since I do not know that we have a convergence of the growth of the tangent map, I require it. So how to do that is the same as for the measure. I force it just by extracting, so by cutting my set TK. So yes.
You use just some kind of Buzzi theorem here, because
Here.
yeah, you want this
Yeah,
to be continuous. You have a measurable map, and you may restrict to a slightly smaller set where you have a continuous map, and you should your sets.
No, but we want the continuity along the when we iterate. So yeah.
What you are proving now,
So I just want to beat the distance of physical measures, SRD measures, but following modifying the proof that I had for another diffeomorphism. Okay. So to force this property for the exponent, I require that for x in tk, the expansion at x is closed to some number of the form that I will write it in the form lambda k times nk. So lambda k is a candidate to be a Lyapunov exponent. So I am asking that all points in Tk have almost the same Lyapunov exponent. And I assume that the lambda k converge to some positive lambda, so still extracting. I'm just saying that I take smaller set, but I can require this after a long time, so I don't lose too much on the size of the set I have to extract. Okay, so let me do that, and then let's see what happens here. So here now, this quantity is about lambda k and k. And what I don't know is that when I can pass to the limit and compare to this quantity. So this we don't know. Okay. So my problem is a problem of continuity of Lyapunov exponents in this setting. I have a sequence of measures which are not invariant, they are empirical measures. I associate a number which measures the expansion that I would like to call Lyapunov exponent if the measure is not invariant. I pass to the limit, and for the limit I have also a Lyapunov exponent, and I want to compare them. Okay. And in general, we don't have continuity of Lyapunov exponents. So this is what we have to do. I am almost done. In the
15 minutes.
Okay. So,
18.
so let me now shift to another work that we did before doing that, where we discuss continuity property of Lyapunov exponent. So this is a work we did before thinking about that, and but then we realized that copying the proof of this other work can be applied to this problem and solve this problem. Okay, so I quit this question and discuss continuity of Lyapunov exponent in a different setting, maybe easier to understand, but this is a way to solve this question. So is it fine with this problem, or do you have still questions about physical measures? No?
We'll use this high smoothness.
Yes, exactly. So to control this continuity of Lyapunov exponent, it's crucial to have a infinity diffeomorphism, and this will appear in the result I will give now. Okay. Okay. So here. So we have measures. For a given system, we consider its invariant measure. And for measures, you can look to different quantities of the entropy, the Lyapunov exponent, and you may look how they vary when you vary the measure. In general, they do not vary continuously. If you're lucky, at least they vary semi-continuously. So and what we will do is to compare the continuity property of the entropy function and of the Lyapunov exponent. So here is the theorem. So again, F is a C-infinity diffeomorphism on a surface. And now you look to ergodic measure. Okay. So you look to a sequence of ergodic measure which converge to another one, ergodic. And assume that the entropy converge. So if the entropy of the new K converges to the entropy of mu, which is positive, then the Lyapunov exponent has to converge. If they do not converge, we can still say something, but we have to assume that the lim sup of the entropy is positive. Then the lim sup of the entropy divided by the entropy of the limit is smaller or equal to the same quantity for the Lyapunov exponent. Okay. So if you're not continuous, this quantity bounds the lack of continuity, and you have a kind of real inequality for the lack of continuity, or the defect of continuity. By the way, for Lyapunov exponent, it's known, it's easy, statistical, that this quantity is f equal to 1, and you have a semi-continuity of the Lyapunov exponent. And so 2 implies 1. You see, if this converges to this is 1, and so this has to be 1. We have a version of this theorem when U is not ergodic also, and in fact this is a main point, and this is what we need for that work, because we don't know that the measure is ergodic, but I won't describe this case. So what I would like to explain is why do we need infinity map? How is it used? So first, one thing I can say is that why don't we have continuity of Lyapunov exponents? So what is the source of discontinuity? For the Lyapunov exponent. So it's the fact that, so when you have an invariant measure with positive entropy, you have an unstable direction at almost every point. Unstable direction. Almost everywhere. And so when you measure the growth of the derivative along this unstable direction, this is the way you get the Lyapunov exponent of the measure. And you can do it also for mu. And you also have an unstable direction. But the point is that the unstable direction for nu k does not converge. It's a measurable direction field. And this measurable field does not converge, even in a measured sense, to the direction for mu. In fact, for each measure, you also have a stable direction, and here a stable direction. And the point is that U, the unstable direction for nu k, will sometimes align with the unstable direction for mu, but sometimes with a stable direction for mu. So there's a measure here when you look to their expansion. Sometimes, for some proportion of the time, they copy the expansion of mu, and so they will copy the Lyapunov exponent of mu. But sometimes, what they see is the other expansion of exponent of mu, which is a contraction. So sometimes you instead to have an expansion, you see a contraction, and so you lose your time, and you don't reach the exponent of EU. Okay. So when you look to the time, and you look to this quantity for typical orbits of nu k, you have so you look to along so you see something like that. So during some period here, you see expansion as for mu. And here you see contraction because you copy the stable direction of mu. And then you wait until you see the expansion of mu that allows compensate. And once you have compensated, then you really see can get again a good expansion and then copy again the expansion of mu. So this period here are period where you lose time, and we could call it neutral period. So you look to the proportion of expansion period. So this occurs with some proportion beta, and then you get that the Lyapunov exponent of mu is just obtained by this period of time. So it's like the Lyapunov exponent of mu times beta. Okay. So the defect of continuity, the ratio I have here is this beta. And I want to show that this beta bounds something for the entropy. So how to control the entropy now? So how to compute the entropy? So the entropy is a complexity. So you count the number of orbits you see, at least to cover. So if it's for a measure UK, you want to cover a set with measure, let's say 1/2. You iterate a large during a long time, and then count the number of itineraries, and you define this way the entropy of UK. This is one way. Here it's good to use curves, to use unstable manifold, because it has appeared in the previous proof. So you have some result by non-Rapéion, classical result, which tells you that to compute the entropy, instead to look at a large set of typical points for the measure, it's enough to just concentrate on point along one unstable curve. So for almost every point X, you look to its unstable manifold, and then let's say of size, you just pick one curve or one interval, and then you look how to cover itineraries from here. So yeah, so let's say delta is a scale, and then you compute so orbit at scale delta during time n itineraries, starting from a set X. So you take the maximum of X in this curve. So it's Y. So that the measure of Y. So again, you have a disintegrated measure. An unstable disintegrated measure for UK along this curve. It's a disintegration. And this is what you play with. And now you look to the growth rate of itineraries starting from Y. And then you take the minimum over when the scale goes to 0. And this is equal to the entropy. what I just want to say that the entropy can be computed by restricting curves to unstable curves, and then compute, as you do usually, the number of itineraries you see inside this curve for point typical for the measure. Okay, so you look to separation of orbits. What we do is not that. I finish with that. So the key tool here is to use more smoothness. And the key tool is what we call Yondin theory. So instead to compute the number of itineraries and of separation of orbits, you take a curve. So let's say it's your unstable curve, and then you iterate. And you want to measure the complexity of this curve. You take a curve gamma, and when you iterate, your curve stretches and folds, or you have something complicated. And what you do is to split the curve into elementary pieces. So you bound the length, you bound the curvature. So you look to the number of pieces with bounded geometry. And you call it, let's say, Rn gamma. And now, when you do that, you look to the exponential growth rate, and it is an upper bound of the entropy. So a way to measure the entropy of UK is less or equal to the exponential growth rate of the number of pieces to cover. So gamma during so iterates of gamma during time n. But what you want is just because you have this measure in UK, you just want to cover a set Y that cover a set Y as before with a large measure with large measure. Well, I don't want to write precisely. What I just want to say that instead to look to how points separate, orbits separate, what you do is to iterate the curve and count the number of pieces with some geometry, bounded geometry, and you count that. And how is this growth? The growth comes from two facts. Comes from either you have a stretch by iteration, but also by folding, because when you fold, the geometry degenerates, then you need to split. And when you have large differentiability, this folding has been bounded by Yondin. We use to have to adapt theory by Yondin, which is so it grows at most as so you look to the log of df divided by r. R is a smoothness. When it's infinited, it goes to 0. So the folds do not count. You just have stretch. And how do you bound the stretch? There are two ways. You may bound by looking at the growth of derivative. And so this is how you link to the Lyapunov exponents. Or you may just say, now I come back to orbit separation and I look to what I have at the limit. At the limit, I have my limit measure. And so I bound by the entropy at the limit measure. I can choose. When I am in, so remember that the orbit now for the measure I'm interested with, UK split in two parts. Some are these neutral periods, some are the expanding period. When I am neutral, I use this one. Just because here the expansion do not contribute. So
right.
Neutral period.
The first word.
During.
Okay.
So here there is no contribution. No contribution. And here, well, I just find the entropy. And here, this occurs with frequency beta. Okay, so this is during expanding time period. Okay, so here the contribution is 0, here is 0, and here I have the entropy during this frequency, and so the entropy of UK is bounded by beta, the entropy of nu. So here I bound this by beta, which is what I want. Okay. So now maybe you understand why the differentiability is used. It's really because we can introduce these tools, which is Youngkin's theory, which is a wonderful tool. Yes, so this is how it was used a lot first in dynamics to show, for instance, Newhouse proved that for infinite diffeomorphism, the entropy is semi-continuous. How does it? Why? Just because Youngkin's theory tells you that the entropy cannot. There is no local contribution of entropy, so you essentially stay at a given scale, and as I told you, at some given scale, the entropy is semi-continuous, and so you get this semi-continuity.
In other words,
Consequence of asymptotic expansion.
Well, yes, but how do you prove the asymptotic expansion?
C infinity implies asymptotic expansion. And here, if you start the entropy with given partition, then you have this semi-continuity.
Yes.
The problem is that entropy counted on finite partitions. When this number of pieces of finite partition tends to increase smaller and smaller, it really converges to entropy.
Yes. So this is also behind our proof, but here, in addition to this, what has been done, for instance, by Newhouse, to control the semi-continuity property here, we played with Youngkin, but at a different level, we play more on the tangent space to link with the Lyapunov exponent and yes. Okay, so that's it. Thank you.
Are there any questions offline or online? Maybe I will ask a question if you have only one physical measure, what does it mean?
Only one physical measure?
Yeah, and also in this context, because you can also define you can define a basin with respect to an attractor. So you can give a topological definition, and then you can ask in that basin how many.
Yes, you may localize the problem. Yes.
And then does it have any? Let's say we know that there is only one physical measure, not several.
Yes.
So does that say something?
I don't know what you want to say. I mean, well, first, you see, we have an assumption to ensure the existence of SRB measures. So, in principle, you may have some physical measure with some basin which do not cover the whole manifold. But it does if the set X that I have introduced, a set of points which have large some positive growth rate, has full volume. So this is what David Gergé added. I wrote the union of the basin of the measure in this case would cover the up to 0 volume, the whole manifold. Then I don't know what you want to.
I want to conclude something on the fact that there is only one.
You want to prove to have a condition where to check that there is only one. Okay. So then we have there are results in that direction. So if you have, for instance, a transitive diffeomorphism, then you have at most one SRB measure. So this is so this has been proved by Tazili-Ures, and we have also proved it again with Jérôme and Omri, because in general it's true for a class of equilibrium measures. When you're transitive, so we split the dynamics into PC that we call homoclinic classes, and when it's transitive, there is at most one such piece, and each piece can only support one equilibrium measure for a given potential, one hyperbolic equilibrium measure for a given potential, and so you may have at most one SRB measure in this case. Yes. Or more generally, well, you may have several ones, but the entropy, if you have an infinite number of SRB measures, their entropy has to go to 0. The number of measures with entropy larger than epsilon is finite. So,
Any other question?
If you have C infinity diffeomorphism discussing the Lagrange expansiveness, which means that you have a pretty symbolic extension.
okay.
Can you somehow use this packet and use this extension?
Okay, so this is a bit what we are doing also, but not with this extension. So you know, all this work in fact started because of something of some result of Omri Sarig more than 10 years ago. He proved a coding for surface diffeomorphism
With how many symbols? Infinitely.
with countable many symbols, but it's not
Yes, symbolic.
symbolic, but okay. And what it does it code? It code the set of measures which are hyperbolic. It doesn't see the measure with zero exponent. But so it codes with a countable Markov shift, the important property that it's Markov. And finite to 1, so it preserves the entropy. So it allows to do to transport the theory for Markov shift to the setting of the surface diffeomorphism when you concentrate on the measures which are hyperbolic. And so One consequence of that, and this is the reason, in fact, we did that, is, for instance, that for to show that for simplity diffeomorphism on surface, if you look to the measure maxima giving the entropy, assuming the entropy is positive, the measure maxima giving the entropy, then they are exponentially mixing and satisfy many limit theorem. So this is because we can we can lift to this countable Markov shift, but then countable Markov shift, the difference with finite one is that they are not always exponentially mixing. So you have a classification of countable Markov shift, and there are the good ones that look similar to the finite ones are those which are very property called SPR, strongly positive recurrent. And so we show this property using this property here. So maybe this is something that Jérôme can tell later.
We are looking forward to that. Okay, thank you very much.